classes and fundamentals of electrical engineering. We were on module 4 where we were discussing signals and systems. In the last few modules sessions, we were talking about the classification of signals and thereafter the systems, because systems are explained using a pair of signals generally. Then we had moved on to linear time invariant system as a class of importance. And then again, impulse response as another model, the other kinds of Laplace transform assisted understanding of the system. And in the last module session, we also talked about the convolution as a very empowering kind of tool that we can use for analysis as also for implementation of systems. Now we have sort of a mop-up such that a little bit of convolution, a little bit of whatever was covered, as also something that is not covered can be discussed, but in the context of gate examination questions. So let's move to the first question, which is from the convolution area. The question is, if UT, RT, you denote the unit step input and unit ramp functions. These are generally the notations for step input and ramp input. In control system parlance, UT is generally considered to be any input. Okay, so but here it is generally in signals system, it is normally the step input. Okay, and if the amplitude is 1, it's a unit step input. So we have the unit step input and unit ramp functions respectively, and UT star RT, which is the convolution between these two signals, their convolution. Then the function UT plus 1 convolution RT minus 2. We had earlier looked at a situation wherein we had an advance of both the signals which were convolving with the time delay of tau. Okay, in this case, there's a delay of 2 time units and an advancement of 1 time unit. Okay, so let's see what the Laplace transform would be, which is what is the function, is given by what. Okay, so we are supposed to find out the function after convolving. So there are two methods. One is of course using the integration method, the other is the Laplace transform method. So let's take the Laplace transform of both. So we see that ys is ut plus 1 convolution. So ut plus 1 has a Laplace transform as given by 1 by s e raised to plus s, because it is an advancement. Okay, multiplied by that is the Laplace transforms can be multiplied. So the Laplace transform of rt minus 2 is as is obvious, is 1 by s square e raised to minus 2s, because there is a two time unit time delay. Okay, so when you multiply them together, it's going to be 1 by s cube into e raised to minus s. You can take the Laplace inverse very easily enough. It is going to be 2 by 2t square, but of course t square by 2, but the problem happens to be that now there is a time delay of minus the time delay of 1 second. So you have ut minus 1, and the t that you got, that is t square by 2 that you got, has to be replaced by t minus 1. Okay, so any t will be replaced by t minus 1 as a consequence of having a time delay as signified by the Laplace quantity of e raised to minus s. I suppose this is clear. So I repeat, first you take as it is, you would have known that there is only one time units delay, because there is an advancement as also a delay of 2 different time units. The advancement is of 1 and the delay is of 2 time units. So definitely the answer would have only one time delay, one time unit delay. Okay? So here we see that we have a ramp multiplying a ramp convolving with a unit step function. So you have the better method is to take the Laplace transform. So we have 1 by s multiplied by 1 by s square, and that gives you 1 by s cube, and the total time delay as e raised to minus s. Okay, so now 1 by s cube is Laplace inverse to t square by 2, and then e raised to minus is accommodated by having not just ut minus 1 but also the t being replaced by minus 1. So t minus 1 whole square by 2 ut minus 1 is going to be the answer. Okay. So let's move to another problem, which is of course something that has been already dealt with. That is the convolution of the function f1t equal to e raised to minus 2t ut, and f2t e raised to minus t ut is equal to. Okay, so we need the function, or in other words, we are not left with the Laplace only. We have to take the Laplace inverse as well. Okay, so e raised to minus 2t gives us 1 by s plus 2, and e raised to t gives us 1 by s plus 1. So the Laplace in the Laplace domain, it is 1 by s plus 2 into 1 by s minus 1. Okay, so now we have to take the Laplace inverse. So we see that there is a residue for 1 by s plus 2, there is a residue a for a by s plus 2 as given by multiplying the entire function by s plus 2, and then substituting s as equal to minus 2. So we have minus 1 by 3 and as a. So a divided by s plus 2 becomes e raised to minus 2t. Okay, so now going on to b by s minus 1, where b happens to be the residue of the partial fraction 1 by s minus 1. So we just multiply the entire function of 1 by s plus 2 into 1 by s minus 1 by s minus 1 to remove s minus 1, and then we substitute for s as equal to 1 in what is left, which is 1 by s plus 2. So that is equal to 1 by 3. So we have both the coefficients have the magnitude is equal to 1 by 3. For e raised to for 1 by s plus 2, the residue happens to be negative. For the other, that is 1 by s minus 1, it is going to be positive. Okay, and the b by s minus 1 or 1 by 3 by s minus 1 converts into e raised to t as the Laplace inverse. Okay, so we have, this is the function that we get after convolving e raised to minus 2t and e raised to t. Okay, so moving on to the third problem, the value of minus infinity to plus infinity integration e raised to minus t delta 2t minus 2, so okay, dt. Okay, so we are having two different situations here. One is of course the Sifting theorem. What does Sifting theorem tell you? That you can always you can sift out the value of a function. In this case, it's e raised to minus t at the point where the impulse is located, so long as you integrate it. Okay, so where you can integrate it from minus infinity to plus infinity, or from any value to any other value, so long as that particular point is taken into consideration. Here the point happens to be, let's see, we are having delta 2t minus 2. So we can take out 2 such that it becomes delta 2 times t minus 1. Okay, why do we take out 2? Because now it indicates what is going to be called as a as a contraction, because c now is equal to 2. Okay, which means that's a contraction. So now we see that the point is located at t equal to 1. Okay, so that is the point of sifting is located at t equal to 1. So what's the value at t equal to 1? We have e raised to minus 1 as the value. Okay, and then when you integrate, you are integrating actually the impulse, and the impulse will always get integrated into its area, which is in this case equal to is in this case equal to 1, but then there is what is called as a contraction as given by 2. Okay, so half times 1. Okay, and there's also already the magnitude of e raised to minus 1, so the answer comes out as equal to 1 by 2e. Okay, so I'll recount the steps once more. Here we have an application of the Sifting theorem. What does Sifting theorem tell us? The Sifting theorem tells us that you can take the integration of a function ft multiplied by an impulse from minus infinity to plus infinity, or from any value to another, or over any range, such that the point at which the impulse is located needs to be picked up. If that's the case, then the value of the function ft will come out multiplied by 1, where 1 will be the area of the impulse. In this case, we have a little more diversion, in the sense that here we are having a contracted impulse. What is meant by contracted impulse? That the area is half of it. Why do we say that the area is half? Because it is given by delta 2 into t minus 1. Why do we say that the impulse is given by delta 2 into t minus 1? Because we have taken out 2 such that whether it's contraction or whether it's expansion can be clear to us. If it is if this value of 2, which is what we called as C in the earlier session, is more than 1, then it's a contraction. If it's less than 1, it's going to be an expansion for the area so long as it is integrated. Okay, an impulse will always give an area equal to 1 if it is not contracted or expanded. Okay, so in this case, now we see that all these concepts are put together in the sense that we are taking the integration from minus infinity to plus infinity. It definitely includes the point at t equal to 1, wherein the value of the function, which is now e raised to minus t, becomes the same as equal to e raised to minus t equal to 1 or e raised to minus 1. And the area is now contracted to 1 by 2. So we are seeing that what comes out as the result, or what can be called as sifted out, is the same. It's not shifting, it's sifting. It's the same as equal to 1 by 2 into e raised to minus 1 or 1 by 2e. Okay, so it's a very interesting application of Sifting theorem. Okay, so let's go to the fourth problem, which also looks like Sifting theorem. The value of the integral minus 5 to 6, minus 5 to 6. As I said earlier, it's not just minus infinity to plus infinity. Even other ranges are applicable so long as the location of the impulses is within the is an integrand. What we see here, we see delta t minus 1. So the impulse is located at t equal to 1. So what's the value of the function ft? It's the function ft is e raised to minus 2t. So at the location of the impulse, we are having e raised to minus 2. Okay, so we see that e raised to minus 2 is there, and then when you integrate from minus 5 to 6, you integrate at the point where this is the coefficient now. This is just the magnitude which is multiplying the impulse which is getting integrated. So the impulse, as it is when you multiply by an impulse, only at a particular point, the functional value of that particular point alone comes out. In this case, we are also integrating, so we are seeing that it has to be multiplied by 1. Okay, unlike in the earlier case where the area was halved. Okay, so we are seeing that e raised to minus 2 into 1 is going to come out. Okay, when you're integrating from minus 5 to 6, so we see that the result is going to be e raised to minus 2. Okay, so both are Sifting theorem applications and very interesting, but also simple applications that we we have covered since they were already given in the GATE examinations. Okay, so now let's move to the fifth problem, which is also a little different. It's a different way of viewing the problem. Okay, what is asked is, consider an LTI system with transfer function hs. So LTI is very, very important because it says that we get an impulse function hs as equal to 1 by s plus s by s plus 4. It means that let's read further, and let me give you another interpretation for this. If the input to the system is cos 3t, so now the input is going to be sinusoidal, which means that now everything is going to work in terms of s is equal to j omega. Okay, or in other words, in this case, omega is equal to 3 because the input is going to be is sinusoidal. Okay, so now we need to work only in terms of frequency. Okay, so omega is now equal to 3, and the steady state output is given as equal to a. There's a magnitude sine 3t plus alpha. Then the value of a is. So this is the question. So what has happened is that this is an LTI system, so the frequency will not change. Okay, so what is going to come out is going to have the same frequency, and that is what is shown here, a sine 3t plus alpha. But at the same time, two things happen as a result of the transfer function working on the input. The input is cos 3t, and what happens is that the transfer function has two ways of operating on it. One, of course, it will change the magnitude, or it will enhance or reduce, or it will give a magnification factor for the amplitude. It will also change it can give rise to a change in the phase angle. So there are two consequences of the impulse work of the transfer function working on the input. So what happens is that now we are, and so what's the impact? Okay, so what happens is that s can be now replaced by 3. Okay, j3. Okay, so we have 1 by j3 and j3 plus 4. So there's a magnitude version, and what is that? There is what is called as 1 by j3 will give you a magnitude equal to 3, and j3 plus 4 will give you a magnitude equal to 4 square plus 3 square, square root of that, that's 5. So 1 by 15. Okay, so a becomes 1 by 15. 3 does not change because it's a linear time invariant system. So sine 3t, and but then there's a change in angle because earlier the input was given as equal to was a cosine function. Now it's a sine function. function. Those not only an angle difference of 90 degrees, there's also an angle difference of alpha. How do you do that? By understanding that that j omega, that is on the denominator we are having j omega, so that's 90 degrees, and then we also have j omega plus j3 plus 4, so tan inverse of 3 by 4 is going to give you another angle, so both these are going to be on the denominator, so minus of 90 minus of the corresponding angle. That's the reason why the cosine has become a sine value. Okay, of course we don't need to do it, but this is the way that it goes. Okay, so because of the sinusoid, I repeat, omega is set as equal to 3, so transfer function works on the input giving a magnitude and a phase angle change. So what is h j omega is the same as equal to 1 by 3 square root of 3 square plus 4 square, which is equal to 1 by 15. So the amplitude now changes from 1, that is the input becomes converted with an amplitude given by 1 by 15. So B is the correct option. There's also a change in angle which is not to be computed, but I suppose it's there in the next problem, that is the sixth one. Okay, so let's read the sixth one. We see that xt is given and yt is coming out. Okay, and what works on the input is going to be s by s plus 1. Unlike in the earlier case, here we are having earlier it was 1 by s by s plus 4. Here it is s by s plus 1. So there is a pole as also a 0 working on the input to create a particular kind of output. So let's see what the problem reads like. The system shown in figure, the input xt is equal to sine t. So omega is equal to 1. So immediately you glean out that the omega is going to be equal to 1. In the steady state, the response yt will be what? Okay, so it's a linear time invariant system, no doubt about it. Okay, and so what we do, we try to see how the transfer function works on the input. So what is the transfer function doing? It is now being converted into hj omega. So what is hj omega? It is the same as equal to j omega divided by j omega plus 1. Okay, so the amplitude version is going to be 1 by square root of 1 plus 1 square root of 1 plus 1, both of them square, so it's going to be 1 by root 2. Okay, so 1 by root 2 is going to be the amplitude that is going to be multiplied to the input to get the output. So 1 by root 2 sine. Now what happens? Okay, let's see if there's an angular change. Of course there is an angle change, because on the numerator we have an angle equal to 90 degrees, because s has been replaced by j omega, so that's 90 degrees. And on the denominator we are having again j1. Okay, so we have j1 plus 1, so 1 tan inverse of 1 by 1, that's equal to 45 degrees. So 90 minus 45, and that is giving us a 45 degrees changeover. And what is it? Since it's going to be a positive angle, because the numerator is plus j and the plus j omega or plus j1, and the denominator is going to be j1 plus 1. So 90 minus 45, that's going to give us 45 degrees. So the option B is going to be the correct answer. I suppose both these problems which are related have explained to you how the transfer function, how these kinds of problems can be done in a different manner, wherein it can be seen that if there is a block working working against the input, then what comes out is going to be the result of the block, the transfer function block working on the input. In this case, we see that the inputs happen to be sinusoids in sinusoidal in nature. So what we do is that we replace s by j omega. Okay, so so omega can be obtained from the input, and the output has the same frequency, but the amplitude has also the phase angle change based on the working of the transfer function block, which is kept within. Okay, so that's the function of the transfer function block. Okay, so we come to the last slide. Okay, so this also seems to be a little okay, perhaps aligned to whatever we have been talking so far. Let a signal a1 sine omega 1t plus phi 1 be applied to a stable linear time invariant system. Okay, so it's a time invariant and also stable system. So we have given a signal a1 sine omega 1 t plus phi 1. So omega 1 will not change. Okay, so even at the output, then the corresponding steady state output be represented as a2. So the amplitude is now a2. That may change. F, that's of course it's a sinusoid or a cosine. It's definitely a sinusoid. It may be a sine function or a cosine function. F omega 2t. So omega 2 has to be equal to omega 1, because it's a linear time invariant system. A linear system never will change the frequency. Okay, plus phi 2 may be might be different from phi 1. Okay, then which of the following statements is true? F is not necessarily a sine or cosine function. That's not true at all. Okay, it has to be a sine or cosine function, right? And it has to be periodic with omega 1 equal to omega 2. Okay, so B option is F must be a sine or cosine function with A1 equal to A2. There's no obligation at all. A1 and A2 will definitely change with respect to A1 so long as the transfer function of the block that comes with comes as a part of the system will affect it. Okay, similarly phi 1 cannot be equal to phi 2, so option C can also be rejected. Okay, so what about the D option D? F must be a sine or cosine. Of course it has to be with omega 1 is equal to omega 2, so obviously we go for the for D option. Okay, so last question. Signal e raised to minus alpha t sin omega t is the input to a real linear time invariant system. Or real means it should be stable. It should never have any outputs going to infinity. Okay, so given k and phi are constants, the output of the system will be of the form k e raised to minus beta t sin vt. Okay, so omega is so the input happens to be e raised to minus alpha t sin omega t, and so the input has two time functions. One is e raised to minus alpha t, so that has to be retained in the output. Its reflections will be found on the output. Similarly, sin omega t will also be available at the output as a sine function or as a cosine function with the omega retained. Similarly, e raised to minus alpha t, so minus alpha t needs to be retained. Okay, so this is no doubt general about the linear time invariant system. Okay, so the output k may be different, but e raised to minus beta t will be the same as e raised to minus alpha t, and sin vt will be sin omega t. A phi can emerge because the transfer function block is working on the input, where beta need not be equal to alpha. No, it has to be equal, so we'll reject that. V need not be equal to omega. No, we'll reject that. Beta equal to alpha and V equal to omega. Okay, we need look no further. That's going to be the correct answer. Okay, so whatever. So the fourth option, that is D option, is also going to be a conglomerate. Okay, so here we discussed three different types of problems. We talked about the convolution again, just a simple adaptation. We also talked about how in two respects. One is of course the fact that you can use any time delays, and you can still find the convolution, because the time delay of each of these functions or advancements will come into the picture in the output as well. Okay, so there is so that's one thing. Second is of course that we can always take any functions Laplace transforms, multiply them together, and then you can take its Laplace inverse to obtain the function or functional value of a convolution result. Okay, so then we moved on to the Sifting theorem, wherein the Sifting theorem is very important in the sense that the impulse is used to sift out the value of a function xt or ft. How? By multiplying it by the impulse and then integrating. Okay, so the area of the impulse has to be picked up. Okay, so or in other words, the point of location of the impulse has to be picked up, because whether you go from minus infinity to plus infinity or whatever time range, if the impulse is picked up, then you're going to get the integrated result as equal to 1 multiplied by the functional value at the point of time where the impulse is located. Okay, so that's so Sifting theorem was discussed, and we also saw that when you are having delta c t, then the result is going to be the 1 by c times the area of what is picked up via the Sifting theorem or by integrating. Okay, so we also looked at the third aspect, wherein a linear time invariant system works on a sinusoidal input such that omega is retained. It works on an exponential such that the coefficient of the exponential is retained, but at the same time what happens is that there is a magnitude change as also a phase angle change is possible. So what about the magnitude change? It will be given by the magnitude of hs, where s is replaced by j omega. Where do you get the omega from? From the sinusoid that is input to the system. Okay, so we also talked about the fact that that there can be a phase angle difference. And what is the phase angle difference? It will be given by Again, while replacing s by j omega, you get all the angle values. So the numerator angle divided minus the denominator angle will give you the total angular change that is happening as a result of the transfer function or the linear time invariant system working on the input, okay, sinusoidal input. So I suppose these three slightly different problems are also nicely nicely adapted, accepted by you, and you'll be able to do such problems. Okay, so thank you.